Well, hello there. This is a lesson about solving systems of equations. This lesson is brought to you by Conalonzo Inc. We are here to help you with all of your math needs. Our goals for today's lesson are to be able to solve a system of equations using any algebraic method. This should be a review. We have talked about this before. We just wanted to review the algebraic methods because we're going to build on that in this unit. We also want to be able to classify a system of equations. Classify is going to be the important word here. And we want to be able to validate a potential solution of a system. So we're going to work on all of these things today. First of all, a linear system, it helps to know what it is made up of multiple lines on the same coordinate plane. So when you're graphing more than one line on the same graph, you now have a system. In this case, a linear system, a system of lines, and the solution of that system is the point of intersection. There may be more than one, but any solution of the system is the point where those lines might cross. Now, let's talk about how to classify a system. A system is classified by how the lines intersect. So we have a couple of different options here when we're talking about linear systems. And I'm being very clear about linear systems because we are eventually going to talk about non-linear systems. Today, we're talking about linear systems, and they can intersect at one point, they can intersect at infinite points, and they can intersect not at all. Okay, we have a couple of different types of lines that we're talking about here. For example, if we have two parallel lines, those lines are not going to cross ever, and we're going to have 0 points of intersection. Therefore, there's no solution to that system, and that system is classified as being inconsistent. Now, when you have a point of intersection, the system is called consistent. And then there's two types of consistent systems. When you have an intersection at one point, so two lines that intersect at only one point, that is called an independent consistent system. You could also have the exact same line being graphed twice. These would intersect at an infinite number of points because they're intersecting at every point. And this is called a consistent and dependent system. You do need to know those classifications. They are important. So you need to know if they intersect at one point, they are consistent and independent. If they intersect at infinite points, they are consistent and dependent. And if they intersect not at all or at 0 points, they are inconsistent, okay? So when you are asked to classify a system, you need to know what these words mean and what that means for how many solutions they have. Now let's talk about some systems here, and we're going to classify these. Okay, we're going to do a little bit of practice here. Looking at number 1 here, where do these lines intersect? Well, very clearly they intersect at one point. Therefore, there's one solution, which means that this is a consistent, independent system. Your teacher may be okay if you abbreviate that, but check first and make sure that your teacher knows what the abbreviation means that you're using, okay? Number 2 here, we have two lines that looks like they're not going to intersect at all, which means that these are parallel lines. Okay, we're talking about parallel lines, which means that we have no solution, which gives us an inconsistent system. Okay, they will never cross, therefore the system is inconsistent. And number 3 here, these are obviously two lines on top of each other. We've got a blue and a reddish purple, whatever, on top of each other. Therefore, these are the same line and they intersect at infinitely many points at every point. Therefore, this is a consistent system because they do intersect, but it is dependent because the two lines are dependent on each other versus where they intersect at one point, they would be independent. I hope you're understanding how to classify the systems and understand what that means for how many solutions they have. Okay, so this solution would have 1 point. This solution would have, or this system, I'm sorry, would have no solution, and this system would have infinitely many solutions, okay? Now let's talk about solving. There's two algebraic methods that we talk about, substitution or elimination. And both have their uses, both have times when they are appropriate. We're going to kind of leave the choice up to you as to which one you want to do when, but kind of know which one makes more sense in a given situation. So substitution is when you are substituting. You're taking one variable and you're substituting in for the other. So you can see here that I have an equation that is x equals 4y plus 5. I've taken that and I've substituted it in to the second equation for the x. And then I go through and I solve and I get a value for y. Once we have y, we do a method that's called back substitution. Where you're substituting the value back into the equation to solve for another variable. So I chose to put my y back into this top equation and to solve for x. Now, notice my answer is an ordered pair. What are we trying to find here? Well, we're trying to find the solution of the system. And we talked about the solution of a system is the point of intersection. Therefore, our solution is a point, and points are always written as ordered pairs. That is actually important, okay? Your solution is not y equals 1, x equals 9. Your solution is the point 9, 1. That's an important distinction to make, okay? Because what we're doing here again is we're solving for a point of intersection. Our answer, our solution should be written as a point. Now, I did not show it here, but I always check my answer before I write it as an ordered pair in the other equation. So I would have put 9 in for x and 1 in for y and make sure that I got 29, which I did. Okay, so I always check my solution. That's called validating. If you remember, that was one of our learning targets, was to validate a solution as the solution of a system. Validating means checking your answer in both equations to be certain that it works. Okay, so first method is substitution. Second method is elimination. Guess what you're doing with elimination? You're eliminating a variable. Okay, and this works really well if the coefficients are the same or if you can make them the same. In this case, I had a 2x and a negative 2x. So I simply added the two equations together because 2x plus negative 2x is 0 x's. I'm able to eliminate x by doing that. And then I just added everything else and I solved. So 3y plus y is 4y, 20 plus 4 is 24, and then I divided 24 by 4 and got 6. Once again, I do that back substitution where I'm taking my value, my one value that I solved for, and I'm substituting it back into an equation to solve for the remaining variable. It does not matter which one you substitute or back substitute, sorry, into. Okay, I always substitute in the top and check in the bottom. That's my method. You don't have to follow it. It's just a nice way of keeping things straight. So I took that 6 and I back substituted into the 2x plus 3y equals 20. I solved for x and I got x equals 1. And then, of course, I checked my answer, which is the ordered pair 1, 6, in that second equation just to make sure that it works. And it does. Okay? So part of this is knowing which algebraic method to use, and we'll talk about that a little bit more as to which one's more appropriate in a situation. Knowing that we need to write our answer as an ordered pair, and then always validating our solution by checking it in the equations. Let's work through a couple together, okay? So we are going to solve this system. Now I'm looking at this system and my variables are not lined up. Everything's kind of a little bit crazy here. But it looks like to me, if I were to rewrite this so that all of my variables were lined up together, which means that I'm switching around the negative 2x and the 3y. It looks to me like elimination would be a very good method here because all I have to do is add the two together. 2x plus negative 2x is going to cancel out. Those are going to eliminate. And then I can simply add everything else, y plus 3y and 10 plus 6. And then I can divide by 4 and I get a solution for y. I get y equals 4. That was actually pretty easy to eliminate there because my x variables were already had the same coefficient. Okay. Now I'm going to back substitute, and like I said, I always plug it into the top one and solve for x. Notice I put 4 in for y. I'm going to subtract 4, and I'm going to divide by 2. Now, my ordered pair, which is my solution, should be 3, 4. But before I circle that and move on, I'm going to check it in this second equation. Now, be really, really careful. Notice that this is 3y minus 2x. So I need to make sure I put things in the right spots and not switch that up, okay? So 3 times 4 is 12, minus 2 times 3 is 6, which is 6, so that checks. I'm going to circle my solution and move on. By the way, if I were classifying this, how would I classify this system? Well, it has 1 point, so we'll try not to write the wrong thing here. This is going to be a consistent independent. And I started to write independent first. The order really is consistent and independent. So make sure that you're writing that the correct way, okay? So because we have one solution, this is a consistent independent system. Let's try another one. Here we have 2 equations. None of them have anything the same, okay? So let's try substitution just for a little bit of practice here, which means I'm going to take this top one and I'm just going to subtract 4y to the other side because it gets x by itself. Now I've got a nice little expression that I can plug into the second equation, and I will be able to solve for y. So I'm going to distribute my 2, and then I'm going to combine like terms. And what I'm noticing here is that negative 8y plus 8y is 0, and I'm left with 20 equals 11. What does that mean? Well, since 20 in fact does not equal 11, these would be parallel lines that would have no solution, okay? We have an inconsistent system here because these would be parallel lines that will never intersect and have no point of intersection. Anytime you get something where the variables go away completely, you either have an inconsistent system with no solution or a dependent system with infinite solutions. And the difference is what you're left with. If you're left with a false statement, it's no solution. If you're left with a true statement, like 20 equals 20, it would be infinite solutions. Do you see the difference there? So still solve, your variables go away, and that's okay. See what you're left with. Are you left with a statement that's true, 5 equals 5, 10 equals 10, negative 3 equals negative 3? Then you have infinite solutions. Or are you left with something that's false, 20 equals 11, or 9 equals 13, or negative 5 equals 72? Those would be no solutions, okay? So if you get your variables to cancel out, that's okay. Just keep going and figure out what kind of system you have. Now, this system that I have here is very clearly set up for substitution because I already have the x equals part. So I'm just going to take that 2y and I'm going to plug it right in for the x, and I am going to solve this for y. My first step again is to distribute. And then I want to combine like terms. So 6y minus 4y is 2y. Notice I didn't cancel my variables this time. I'm good to go. And we're going to subtract 3 and divide by 2. And we get a value of y that equals 4. Now I want to back substitute that into the top equation for y because it's going to be easy to solve for. All I have to multiply is 2 times 4 plus 1, and I get an answer of 9. Now, that means that my solution is 9, 4, but I want to check this in the bottom equation just to make sure that it works. So I'm going to plug 9 in for x, I'm going to plug 4 in for y, and I'm going to evaluate to see if I get 11. Well, 9 times 3 is 27, 4 times 4 is 16, and if I take 27 minus 16, I do get 11. So this checks. I have a consistent independent system with one solution. We'll try one more here. Let's try, oh, this is a typo. Let me add my y here. Let's try this one by elimination. That may be the easiest, and I kind of want to practice the multiplication part, okay? So sometimes you have a system where substitution is not going to be easy to do, and you don't have any variables that are the same. You can multiply the equations in order to make I wanted my x's or my y's to eliminate, I could multiply both equations by something to make those the same. I've done a lot of solving for x today, so I think I'm going to try to get the y's the same. So I'm going to multiply this top equation by 2 and this bottom equation by 3. And watch what happens. When I multiply the top equation by 2, I get 18x minus 12y equals 48. When I multiply the bottom equation by 3, I get 18x minus 12y equals 48. Whoa! Now my variables are the same. In fact, both variables are the same. So when I subtract, I'm actually going to end up canceling both of them out. And I'm going to get 0 equals, what is 48 minus 48? It is also 0. I have a true statement here. So remember we were talking about either no solution or infinite solutions? This one is going to be an infinite solutions. These are actually the same line, which obviously you can tell because the equations are the same when we multiply them. So sometimes we need to multiply in order to get the variables to be the same so they can eliminate, or in this case, both can eliminate, and we can solve. Here we have, remember, a consistent dependent system that has infinite many solutions. I hope you're feeling like you can solve a system algebraically. I hope this is a good review for you, whether you're doing elimination or substitution. I hope you also understand how to classify a system, and you can tell whether it's going to have one solution, infinite solutions, or no solutions, and what kind of system it is. We are here for you, so if you need anything, let us know. This is Con Alonso Inc., Miss Con, Miss Alonso. We are happy to help you. Please check in with us and let us know what we can do. Always take care and have fun doing math.